We're going to go over the hardware setup, software setup, and all that kind of stuff, which is great, and talk about, RZ10X in the context of photometry, maybe the differences. I don't know if you've ever used RZ5P system, but at the end there is this manual, which is basically going to go over goes over everything that I'm going to talk about today, actually in more detail. But of course, it's easier to learn when you're, communicating with somebody. But, once you have that context, you can go back and check out this manual and it'll walk you through everything in case you forget anything. You can, of course, email me with questions, but the manual is pretty comprehensive. All right, so first things first, we have the RZ10X, it's on. So I'm going to go to zBusMon, and then I'm going to press this transfer test, and that's going to basically just tell me whether or not I'm communicating properly with the system. Anytime you update the drivers or anything on the RZ10X, you'll have to update the microcode in zBusMon, which is this V95 thing down here. Right now it's white because it is matching the driver code. If it wasn't, it'd be red. So there's instructions online for all that kind of stuff, but I just start there. All right, now we'll head over to Synapse. All right, so here's Synapse. If I go to menu, edit rig, here's where my hardware shows up. We have the RZ10X, 3 DSPs, that's all well and good. The DSPs are basically the processing cards inside the RZ10X. So there's nothing to do here. The only thing you would end up doing is if you wanted to add a camera, like a USB camera, for example, you would right click here and say add cam. And then you can add a USB camera that way. Pretty straightforward. Now, in the Space Synapse menu, all right, we have no experiment or subject setup. And okay, I guess this is a fresh computer entirely. So basically what we'll want to do is make a new experiment and a new subject, because right now we can't record anything because we don't have either of those defined. So if I click on the experiment name, I'll just say new, and we'll just call it setup. And now I'll make a new subject. All right, so now I have a subject and an experiment name, and now this record button is available to me. Now, why is that the case? Well, the way that the data is saved, and we'll get to this later, but the way the data is saved is basically there's this folder of tanks, and then inside the tanks are these individual blocks, which are your recordings, and inside the blocks are individual files that make up the block. And we'll see this later. But anyways, the way it's structured is that the tank inherits the experiment name, and then each recording inherits the subject name and then the date it was created. And this will make more sense once we see some recordings, but that's just a little context as to why the record button was gone before we, if I make any of these blank, the record button goes away. Okay, so what we see in the processing tree first is this RZ10X. This is, of course, our main processor. And what we want to do is just go through the tabs and understand them. So on this main tab for photometry, unless you're doing like eFiz or something else, this device rate can stay at 6K. For photometry, 6 kilohertz is plenty. I mean, you're generating up to maybe a 500 hertz sine wave modulation for modulating these LEDs. So sampling it at 6K is going to give you a nice clean sine wave. So you're good there. If you wanted to generate tones or record something beyond like 3 kilohertz in terms of frequency content, then you'd have to bump that up. You don't need to probably touch the load optimization. If you do, then I'd be involved. This tick store is basically just a 1 second tick mark on your plot. You can have it on, you can have it off. It doesn't really matter. That doesn't do too much. The important thing on this page probably is this runtime notes. So if I click notes plus epochs, basically you can make some comma delimited notes like air puff, injection, tail pinch, food drop, etc. And basically during record mode, there'll be preset buttons that you can punch, and then it'll timestamp when that happened with the associated note filing code. So if you're doing some, in vivo testing, and it's not sort of well time locked to some sort of behavioral event or something, and you're just doing air puffs and you want to do some sort of trial event based averaging, then you can use these runtime notes to do that. So you can see when I made a change, this commit button showed up. Anytime you make a change in Synapse, you press commit, and that's gonna basically, in this revision log, track all the changes that you've ever made. So it starts at 17, whatever. Sometimes it starts at random numbers, but in any case, you can see here, I added some record notes, okay? If you wanted to go back in time ever, you can revert back to an old version of the experiment. I'll click on here, there's no runtime notes. And then let's say, oops, I didn't want to do that. I go back to this other edit that I did, and now they're back. There's a database underneath that controls all of that. For the RZ10X, what you want to do is once you're plugged in and communicated, you want to go to this Lux tab and press detect hardware. What this is going to do is it's going to ping the RZ10X and basically figure out what LEDs, what sensors you have connected. So what do we have connected here? We have a 405, 465 for your ISO SPEC stick control and for your calcium signal or whatever, D-light, whatever. Over here, driver 3 is empty, so it has an M8 connector, and M8 connectors connecting from the RZ10X to an external LED would be the traditional way of doing it. The sensor A and the sensor C both have photo sensors in them, PS1 photo sensors. And then Sen B here has a B and C, and Sen D has a PM1. So this PM1 is a power meter, and you can basically access that from the top bank or the lower bank. However, traditionally, when you add a photometry gizmo, which we'll see in a second, each row talks to only one photometry gizmo. So the only special device that talks across gizmos is this PM1. And then this BNC here can be accessed as an input if you have some sort of random signal coming in. Otherwise, you just leave it alone. If you ever make a change, so for example, if you swap LEDs, add an LED, add a photo sensor, what have you, you would have to redetect the hardware. Now, the cool thing is, and we'll see in a second, once I add a photometry gizmo, it's going to automatically recognize what I have in each row. Going to this digital I/O, so this is important in photometry for a lot of people. This digital I/O is going to be your input-output for external devices that send TTL communications, behavioral codes. Very common thing is maybe Med Associates, Harvard Apparatus, Lafayette, something like that, where you hook up maybe like a DB25 cable to the front DB25 port of the RZ10X. You'll see there's a DB25 connector and it says digital I/O. There's also 4 BNCs labeled 0, 1, 2, and 3. So the DB25 connector talks to all 24 of these bits. The front BNCs are mapped to these 4 individual bits right here, which are bit addressable, so you can capture individual TTLs. Typically, with Med Associates, you'll enable port A at the very least, and then you can either group port C as a single port or have them all bit addressable, but let's just worry about port A right now. You enable it. For Med Associates, they go from 5 to 0 when something happens, so you typically want to invert it because it's easier to think of it as going from low to high. And then you just add this epoch store here, and then it'll capture the bit code coming in. So what's a bit code? Well, port A monitors all 8 bits at once. So if I jump here really quickly and go to tdt.com, hardware manuals, processors, RZ10X, on this digital I/O here, what you'll see is port A is over here in pin 6, 619. This section right here is port A. And basically what happens is all 8 of these bits are monitored at once. So when you have an input coming in, let's say Med Associates, which is hooked up via a DB25 cable here and here, let's say a lever gets pressed and then Med Associates is 1, 1, 1, 0, 1, 1, 1, 1, right? So you have bits 0, 1, 2, 3, 4, 5, 6, 7. And then when the lever press happened, you know, bit 4 over here gets flipped from a 1 to a 0. What's going to happen is, well, technically I inverted everything. So the way it would look is 0, 0, 0, 1, 0, 0, 0, 0. And what you would get reported is in Synapse, you'd see a 0. And then when the lever press happened, let's see, this is 2 to the 0. So that's, let's see, 1, 2, 4, 8, 16. You get a value of 16 coming through. So when that lever press happened, you get a 16. And then when it turned off, you get a 0. Does that make sense?
Yep.
It'll make a lot more sense too once it's contextualized. But in any case, that's sort of what the port A is doing. Now these port C's over here are bit addressable, which means you can monitor individual bits instead of the whole byte at once. So when you get something coming in, you'll get the onset and the offset. And the way you would enable that is boom, and then maybe consider inverting it depending on what the signal is. If it's for meta associates, you almost always invert it, and then you press commit, and then that makes a change and it captures it, and that's all you have to do there. Most of the time for photometry, especially on the RZ10X, you're not going to access these. These are analog input, analog output. That's a little bit about the RZ10X. The next step is to add the photometry gizmo to the bank we want to talk to. In this case, we'll just target the upper bank, but we're going to press specialized. So this tree over here is the gizmo tree, and it basically has some of your gizmos that you have available to you. Not all of them, because Synapse actually will prune this list based on available input and output connections. But here's our photometry gizmo. One little neat thing here is if you're ever curious about a gizmo, you can click this question mark here and then click on a gizmo, and then it brings up a little bit like a little slideshow telling you a little bit more about that gizmo and typical input-output connections. But in any case, this is photometry, so we're going to double click here. It's going to tie itself to the RZ10X. You, for the most part, want it always tied to this enable line, which means it'll be active. This green thing is a logic signal. So this enable line is a special line on the RZ10X. You'll see here that there are a couple of different available connections. For photometry, most of the time you want it tied to enable, but these different connections, enable is something where when you start the recording, it's a logic signal that just goes high and stays high. Reset is a once sample logic signal that pulses at the very start of your recording. Sweep fire is something that ticks every 1 second. So you get a logic pulse every 1 second. And then these are your digital inputs. And those are the only available connections to you because this requires a logic input. And those are the only logic signals available. So that's that. Now, the difference between this blue and green here, by the way, this green is logic. This is a floating point signal. This is sort of getting into the weeds a little bit, but that's a little bit about what this picture is and why it matters. In any case, this auto connects to the upper bank for you. And then if you're at a second photometry gizmo, double click here, it'll tie itself to the lower bank. So for the most part, you don't need to worry about it. But for the keenly observant here, you'll see that the difference here is, look at how many logic things I have here, and I have like one here. And for the photometry, it goes away depending on what I click on. So Synapse is pruning that whole list for you. In any case, let me delete the second photometry gizmo, go back here. All right, so we have our drivers connected here. We don't have a third driver, so we can disable that. But we have this 405 and the 465, so those are our LEDs that auto-populates the name there. This max current, most of the time, you'll have it set to 200. That's just the maximum driving current for that LED. If you have to go higher, then we can bump that up. But for photometry, probably 200 is going to be okay. These frequencies down here are your demodulation frequencies. So for lock-in amplification, the way that it works is you modulate these LEDs, and these LEDs are running simultaneously, and you're sending light of different wavelengths down the same fiber. So what we need to do is we need to modulate them, because on our photosensor, when the light comes back out, so, we send light down, stuff happens in the brain, light comes back out to a photosensor, the photosensor sends a signal to the RZ10x. Well, we need to pick out exactly what's changing in the 405 and 465 return signals. And the way we do that is we pick up sort of the frequency content on the return signal. So the photosensor has 210 hertz, 330 hertz, 60 hertz, 120 hertz, a bunch of garbage on it too. And basically we pick out through this thing called lock-in amplification, how much of 210 hertz or how much of 330 hertz is on that return signal. And then you can monitor how much is the amplitude of that signal is changing. So that's why we're driving these at different frequencies. And you can change that too. You can make these driver frequencies different as long as they're not multiples of each other or multiples of 60 hertz. The reason why you don't do multiple of 60 hertz is because that's what your wall power is at. This level here is the peak to peak level of your driver LED modulation. So typically when you need to change the power of your LED, and we'll talk about power later, you would be changing a level. And then the offset here should probably never drop below 5. For these LEDs, they're modulating like this, but they have a DC offset that's needed in order to stay on. What happens is if the DC offset's too low, then the LED might turn off for part of its modulation cycle, which would break the lock-in amplification. So that's important there. As a matter of fact, you can just click this auto calculate offsets and never have to really worry about that, because it'll just set it for you. So that's a little bit about that. The launch power estimate, I never use that. It'll basically try and estimate the transmission % loss in your optical chain. So here are our sensors. We only have one photo sensor, so it populates A and B. One of them is a B and C. If you wanted to, for example, use an external photo sensor, you could do that. But in general, the PS1's in the Sen A position, and then you can have this checked here. The clip threshold, we know for the PS1 that it's 9.5, so you don't need to calibrate the clip threshold at all. If you had an external photo sensor, you would be changing the clip threshold based on, when it saturates, which we can, go over if that's ever the case. The important thing here, besides just activating the correct one, is this filter order. I would say 6 is a good filter order. That's just the steepness of a low pass filter that's on the demodulated signal. And then the default low pass is at 6 hertz, which is pretty much good for most, I would say most sensors. They're getting a little faster, so maybe you can always bump this up to 10 or something like that. But in general, Gefies are really slow, so 6 hertz should be able to finally capture all of your signal. It's a low pass filter on your demodulated signal. So, GCamp 6, has a rising time of like a couple hundred milliseconds. So having a low pass filter at 6 hertz is totally fine. GCamp 8F might be a little bit faster, so maybe you bump this up to get a higher resolution. The lower this is, the smoother your signal is, but that'll also, attenuate content beyond, for example, 2 hertz, 3 hertz, 4 hertz, depending on what the corner frequency is. So 6 is fine. If anything, go up, don't go down. This demodulators tab is going to control a couple things. If you had a second light over here, this driver 3 would be active and the sensor B would be active, and you would set up the table appropriately to say, all right, I want to demodulate my 405 signal with the signal on sensor A, my 465 on the sensor A signal. That's that lock-in amplification I told you about. And then if you had a second sensor here at 560, that would be picked up on an additional sensor B. So you'd say only demodulate 560 with my sensor B. But you only have 2 lights right now, 1 photo sensor, so the default table, totally fine. Use calculated outputs if you wanted to do some sort of like online normalization. It's not really a delta F over F you would publish with, but you could do this DFF here and even subtract it with the DFF of another signal. And it's doing the DFF by making the F0 the mean of a moving 5-second window. It's, all that's going to do is normalize your signal for you. It's going to look very similar to the demodulated signal as is. So you can have it, you can not have it, doesn't matter. In these Lux options, you have this thing called timing control. What basically that is it is a sort of a pulse generator for if you're doing longer recordings. You can turn the LEDs on for a set period of time, turn them off for a set period of time, and do that for a set number of repeats. So people who record more than maybe 1 to 2 hours are going to be using this because you don't want to bleach your Gephi. And so, you know, you turn the LEDs off after like 30 minutes and then turn them on 30 minutes later, something like that. So that's what these timing controls do. This target range right here is going to control when you do power measurements. There's a little bar graph, and it's just a visual indicator. I just leave it at 10. Doesn't control anything. It's just a dummy indicator. And then this assigned Lux IO bank, it's tied to the upper bank. I don't see typically a reason why to change that. Over here in this miscellaneous, you can store the driver signals or not. There's really no reason unless you're doing your own demodulation. And so, you know, that's all that that does here. The only special thing about this tab is if you want your drivers on immediately when you start runtime, you can click this button and it will do that. So that's the photometry gizmo. Now, I guess the next step is to talk about the physical connections from the RZ10x to the Minikube to the photo sensors and subject. So the most important thing is making sure that you have the right cables in the right spots and that the cables are connected properly. So these cables, if I go back here, photometry guide, let's go to the getting started. These cables have a little notch and key mechanism, and you have to make sure that those are aligned. So there's a little metal bump on these FC, this is called an FCM connector. And then this is the FC connector. They have a little bump here and a little notch here, and then they have to be aligned. So in the TDT Lux cable kit, you're going to connect the 200 micron cables from the 405 and 465 to the appropriate input ports, maybe the IE and E1 ports, respectively, of the Minikube. If you have your own cables, that's fine too. But if you have the Lux cable kit, those are going to connect there. And then the subject cable is the subject cable. In the Lux cable kit, there is a 400 micron cable that can serve as a pseudo subject cable, which we'll get to in a second when we do power measurements. And then you have a 600 micron cable that will go from your F1 port, which is the fluorescent output port, to your PS1 in sensor A. Let's just go to preview. So first things first, let me auto scale, and then I'm going to right click this 5FO tab and split that over to the right. Whoops. Missed that. Let's merge it down, right click, split right. So what I'm seeing over here is these are that's my note epoch. You can see my runtime recording notes, only available during record mode, but here are the preset buttons. That's my port A input for the digital IO. These are bits C0, C1. If you activate all the bits, of course, you'd see more. This is my demodulated 405 signal. This is my demodulated 465 signal. Now, there's nothing happening right now, but you're going to get, this is what we call lock-in amplification or demodulation noise. Basically, you know, it's going to not be non-zero because you have this noisy photo sensor here, and I'm sure there's a little bit of 210 hertz and a little bit of 330 hertz on the signal, even if it's a tiny bit. But once we turn the lights on, you'll see that this jumps, you know, it should jump way up depending on how bright the signal is or what you're connected to. You see this jump way up. Now you can auto scale, or you can hold shift and drag like this, and then hold control and drag like this. Now, it wasn't much of a jump, probably because we're not pointed at anything fluorescent in particular, but we'll get to that in a second. So auto scale, yeah, auto scale sometimes fails. to do a good job. And so I like to hold shift and drag like that. In any case, this is our raw photosensor signal. Here you can see it picked up a little bit of the DC shift when I turn the light on and off like this, boom, and then boom. So that's pretty straightforward. Of course, here's where I control whether lights turn on and off. Here's the corner frequency for that low pass filter I talked about. Here's where I change the peak to peak level, which we'll see once we hook up the power meter, we'll control the overall power. Now, you can't say, oh, 10 milliamps equals 10 microwatts. You know, it all depends empirically on the optical chain, and each optical chain is going to be different. So what we want to do first and foremost is just get an idea roughly of the power that we're going to be using at the tip of our fiber. So in the Lux cable kit, there should be a 400 micron FCFC pseudo subject cable, which you can hook up to your sample port of the Minikube and then plug the other end into the PM1, which is on your sensor D of the RZ10x. And this is just going to give us an idea roughly of what the power is. Now, this is only valid if your subject cables are the same core diameter as the cable that you use to estimate the power. So in the case of the cable we gave you, it's 400 microns. Your subject cables would have to have a 400 micron core diameter. Otherwise, not going to be a great estimate. This is going to be for estimating the power, you know, giving you a ballpark. Are my lights working? How much power is coming out of this fiber tip? And then your subject cable is going to be very similar. The issue with the PM1 is there's not a good way to stick that MF connector on your actual subject cable into the PM1 and get a good estimate, because it depends on the depth and stuff like that. Now, I know your group has external power meters, so you can use those as well. We're working on adapters for the MF cable. In any case, all right, so we hooked up the FCFC connector from the sample port of the Minikube to the PM1. I'm going to turn these lights on. All right, something's not correct here. So let's check to make sure that we connected from the sample port to the PM1, which is on SendD. Now, the reason why I knew something was wrong is because the PM1 has fluorescent slides in them. So when I turned on the LEDs, it didn't jump up crazy like it did just now, which you would expect. So again, holding shift, dragging, you can see here, really jumps up. Or I can auto scale like that, and then it'll, you know, hit where I'm looking for. Now, one thing that's important to note is, all right, so when we're doing this, you know, PM1 testing, I need to activate this power meter right here. But the first thing you'll see is that these numbers over here jump up. Mm-hmm. This is your PS1 photo sensor. Most of the time, this is what you care about. But when you're doing power meter testing, you click this power meter here, and the only thing you care about is actually the PM1 bar, because what can happen is you can actually end up clipping the PS1 photo sensor. So you want to just ignore the quality factor and the values coming out here. We'll talk about these later when we're actually doing fluorescent testing. One thing to note here is that these values that you see here in the, you know, this 1730 and stuff like that, those correspond to the amplitudes that you're seeing over here. And then the values over here in the PM1, again, I'd click this power meter button here, toggle that on and off, only available in preview mode. The values you care about right now are these power measurements in microwatts right over here. So again, we just so happen to be lucky that we're not clipping, but if I were to bump this up, for example, to like 50, you'll see here we start to clip. We're saturating the photo sensor. You'll see this quality factor drop. So some people look at that and say, oh, bad, but no, because we're in the PM1, so we don't care about the PS1 bar graph right now. In any case, let me go back down to 10. All right, so looking at the right side bar, what do we see? we have this yellow, green, red. Remember that power target range of 10 microwatts I talked about earlier? That's what this green thing is. It doesn't mean anything. It's arbitrary. All that you care about really is this number that you're seeing here. So for photometry, it really depends on what you're using, but typically I recommend 10 to 30 microwatts is a good starting point for most things. D-Light, maybe a little bit on the higher end, 30 is good. G-Camp, 10 to 20 to 30 is totally fine. So what you'll see here is, you change the power over here and then the level, you change the level and then the power goes up. So for example, 25 is a fine starting point. Let's start there and we'll say, okay, 21 milliamp peak to peak modulation on my 465 LED is about 25 microwatts measured through this particular cable. Unless you have issues with the actual subject cable, it should be pretty good ballpark estimate that you're running about 25. You should use your external power meter to verify though. In any case, all right, we can turn this one on. It doesn't, they can both be on, by the way. So I don't know why I turned that off. Old habit, because I was talking about external power meters, which you have to run one light at a time. So the 405, and this is typical, it's going to run a little bit colder than the 465. That being said, you probably don't even need to run the 405 as hot as the 465 because all it needs to do is pick up bleaching if it's there and motion artifact if it's there. And this is something that you'll sort of get a better grip on once you're actually doing an in vivo recording. You'll see some signal maybe on the 465. And if you don't see anything on the 405, let's say it's flattish, maybe bump up the 405 and try and figure out whether you're actually seeing a real signal or whether it's motion artifact. That's something that once you have an animal, it'll make a lot more sense. It's hard to visualize if you've never seen it before, though, just, talking about it in the abstract. In any case, 20 and 25, that sounds pretty good. So I'm happy with those levels. We can turn those off. And once we're done with the power meter, we just toggle that off. One thing I want to talk about real quick is this Q factor, this quality factor. What that's measuring is basically the amount of return fluorescence that you're seeing at that particular driver frequency. So with the Q factor of 99%, what you're seeing is really nice, clean 330 hertz signal, and that the signal to noise, so the background noise is a certain amount, and then the 330 hertz content on that signal is much higher than the background noise. So what you get is this high signal to noise on the, so it's always going to be Q factor here, but here you can toggle this between Q and signal to noise over here. I just leave it as Q factor. It's really a distortion metric. So if the Q factor is low, that means you have a distorted, 330 hertz or 210 hertz. And you'll see that, yes, that is the case over here, because since we're clipping on the top end, your signal actually looks like this. And so you're not picking up 330 hertz because that's not 330 hertz because it's flat at the top. Or if you have such a low signal, and this happens sometimes, if you have such a low signal that relative to the background noise, it ain't much. So that happens a lot when you're inside of the animal. And for example, let's go to this troubleshooting page. Can't get a response. A lot of the time, if there's an air gap in between the tip of your fiber and the top of your optical implant, air is the worst enemy of your signal because it'll attenuate it. So if there's an air gap, that's a big problem. So a lot of the time when you plug in an animal, the Q factor might be 92, 93%. And then what that means is that you're not picking up a very bright return signal because the background noise and the signal you care about at 210, 330 or whatever are comparable. In any case, okay, the other thing that we see here is this fiber bleaching. The default here actually should be set to, I would say 4 hours would be the minimum. Sorry, the maximum that I would do. And typically, for fiber bleaching, probably can get away with doing 1 hour, 1 to 2 hours a week. But basically, what is fiber bleaching? Well, these cables aren't perfect, so they have these, they have autofluorescence on them. And what fiber bleaching does is you're going to hook up the subject cable in particular. You don't really need to hook up the other cables, but you take the subject cable, hook it up directly to your 465 LED. Run this fiber bleaching for 1 to 2 hours. 1 hour should be fine because it's an exponential process. So you blast a bunch of light through it, obviously making sure that the cable's not anywhere where someone can accidentally be staring at it. And what happens is, the amount of autofluorescence on this cable is going to reduce by like 80% in the first hour. And then, another additional 10% would be another hour. Another additional 2% would be another hour. So it really falls off. And then the autofluorescence in the cable recovers at a much slower time scale, on the scale of days to weeks. So if you photo bleach your cable like once a week, you should be pretty good to go. The official recommendation is to do it every day, but that's a bit excessive. In any case, what you do is, again, hook the fiber directly up to the LED, the 465 LED, and you'll turn this on. And then once you're ready to bleach, which I'm not going to do because it's going to blast light through, you'll press start, and then it has this idle when done, which means Synapse will go from preview mode to idle mode when you're finished. So it's a good thing to do. Okay, we can exit bleaching over here. All right, that's all great. So the next step is going to be to swap out that FC to FC cable that we're now using on the PM1, plug in your regular subject cable. And by the way, if you have a rotary joint, you want to bleach through the rotary joint connection as well. The other important thing to note is if you have a rotary joint, you want to measure the power from the output of the rotary joint to the PM1. So if you were to, for example, use that FC cable that you used earlier, I said go from the sample port to the PM1. For people who have a rotary joint, you'd want to go from the output of your rotary joint to the PM1, because rotary joints can have associated loss of signal and light power through them. Okay, so now we're hooked up from the sample port to the regular subject cable. So I'll turn these back on. What you'll see is, it's going to be a lot lower in terms of signal. That's okay. We're not pointed at anything that's bright and fluorescent. And then you'll see as a result, the Q factor is very low. But what are we going to do now? What we're going to do is we're going to get a piece of paper, scribble some highlighter on it, and then we'll watch the signal change. So what we want in this highlighter test, which is, it's a silly little benchtop test, but it's helpful. We want a surface that's black. We want a white piece of paper, and we want some yellow highlighter. So scribble maybe a strip of yellow on the white piece of paper. And what we're going to do is the black surface is going to be your control, right? Because it's black, it's not going to fluoresce really. There's little to no reflection. So you're going to take the fiber tip and maybe, 2 or 3 centimeters. Okay, you have fluorescence lights too. That's great. But the highlighter test, same deal. You're going to take the fiber tip and you're going to maybe 2 or 3 centimeters hovered over the black surface. So we'll turn these LEDs on. Okay, and now what we're going to do is move over to the white surface, and you'll see the 405 increase primarily. So I'll hold shift and drag, and then go back to black. Okay, you get a tiny bump in the 465, but what you'll see is once we go over the the yellow highlighter, that the 465 jumps up dramatically. So go over the yellow surface now. Yeah, and it goes way, way, way up. So the relative magnitude of change here is much more on the 465. Go back to black. All right, now go over white. now black. Okay, and now yellow. Perfect, now back to black. So the point of this test is to show you how the lock-in amplification is working. Basically, over the black surface, nothing too crazy is happening. Over the white surface, only the 405 is sort of reflecting and picking up. And then over the yellow, both of them are going to pick up. Now, if you have fluorescent slides, what you do, you can do the same thing. That's actually kind of what the PM1 is doing. But basically what this is showing you is, okay, with the same two colors shining on the same fiber, I can distinguish different signals. Now it's just a dumb little test where, okay, why does 4 or 5 increase over the white? It works that way. And that's fine, it is what it is. But it's showing you that there's differences here. Again, there was a very tiny little bump here, but it's just a silly little benchtop test. Doesn't matter. In any case, lock-in amplification, it's looking good, it's working. We're happy with how this is functioning. Now, one common thing I do see when people do this benchtop test is if the power is too high or they get too close to the yellow, what will happen is they'll end up clipping. So actually, let's try and do that real quick. So take the fiber and get really close to the yellow. Yep, and so you're clipping, and what happens is when you clip, you'll see your signal drops sometimes to 0 if you're clipping all the way. You get a flat line here, back up a little bit. You'll see when you're not clipping that the signal returns. And why is that? It's because when you have a flat photosensor line, when you're saturating, there's no 210, no 330, so you have no signal. So you get a dropout in your demodulated signal. And it was quick, but this will also go red if you're clipping. So that's a little bit about the highlighter test. Now, what I want to do is just quickly press record here and take a look at that tank block structure I mentioned earlier. Okay, 2 seconds, totally fine. Doesn't really matter. What I'm going to do is click this ... over here, and that's going to bring me to this history dialog, also accessible through the menu history. And this, you can see, is the recording we just did. If I click previews, it also has a list of previews, but here's the recording that I just did. I can right click and I can say go to data folder on disk. All right, this is bringing us to a set location here. That, by the way, is set in the menu preferences. But you have a D drive, so you should use that as your data dump. But basically, here's the structure. I have this tanks folder, and you have this setup right here. That's the experiment name. So I double click here. Here's my subject name and the date that it was created. So this is my recording. Double click here. And then here are my recording files. Now, all of these constitute your recording file. The most important ones are this TEV and TSQ file, but there are other very important ones here too. As a matter of fact, this TIN file, if I unzip it, it's really a zip file, so I can rename it. So let's say you transfer recordings between computers, or let's say you, for example, lose a copy of your experiment. This TIN file, if I unzip it, actually has copies of your experiment in them. So that can be very helpful as well. Another cool thing about this history dialog, if I right click, say view data in OpenScope, drag this over here, right click the gray space, size to grid, press animate, highlight here. I'm right click, maybe hide this because we don't care too much about it. It's just going to replay the data, kind of like the Synapse flow plot. Again, it was 3 seconds, so nothing too crazy, but you can replay the data here. And for people who have videos and stuff like that, you'll also use OpenScope for maybe scoring videos, but we don't have a USB cam in this case. So press no there. This history dialog, when you go to import the data into either Python or MATLAB, which we have SDKs for. If I go back to the Knowledge Hub, go to offline data analysis tools, we have MATLAB tools, Python tools. I'm a MATLAB guy just because it's easier to do matrices things, in my opinion. Well, plotting is actually the easier thing that I care about. But in any case, you could use either of those. And we have these functions to input the data and read them. And for both of those functions, the arguments end up being the path that you use. So if I go here, it's this full file path over here, or you can copy the path to clipboard here and use that, because if I go to Notepad, I'll just paste it into here. You'll see that it copied the file there. Now, the most important thing is in Python, when you go to import the data, that these slashes need to be reversed, or you have double slashes. It doesn't like the file path where the slashes are the backward slash. So that's a little bit about that, a little bit about OpenScope. Again, I showed you how to do the camera earlier. That's a big thing that people like to use is a USB camera. You can do up to 2 USB cameras in Synapse. So let's go to menu, edit rig, right click, add cam, and then right click, add cam. Now the important thing is for the second camera that you say USB ID 1, so it tries to recognize it on a different USB bus. All right, this one is connected. Go to a preview over here. Okay, it's a monochromatic camera. It shows up here. That's all. That's wonderful. You can change the frame rate if you want. Now, I did notice that the free run rate was a little bit lower than 10. So you might not want to run it at, like, for example, 20. Try 10. If you get some drop frames, then I'll show you in preview. It'll tell you if you're dropping frames or not. So here's our cam. Split that over to the left, maybe. So, okay, it's going to hover around 10. Doing a pretty good job. Cam 1. All right, here's our cam 1. We can drag that over here. Right click, split up. We got our 2 cameras over here. That's wonderful. If it ever drops frames, it'll tell you here. What you'll get here, if I zoom in, are, these are our cameras. You'll see these are not static 10 FPS. So, the frame rate's going to vary a little bit, which means that if you're using like VLC Media Player or Windows Media Player, it might estimate the time wrong because it'll either assume a certain FPS, which it's not, or there'll be a little bit of variability in each of the frames. So whenever you need to, let's say, score data later on, which we're not going to get into now, that's something we can talk about. In any case, one thing I really want to show you real quick, let's do a very short recording. Okay, 3 seconds, we're happy. Go back to that history dialog over here, right click, view data in OpenScope. If I go to view video viewer, my 2 videos pop up here, and when I press animate, it'll have the timestamps of when each of the frames were grabbed. More on that, at a later date. The last most important thing I wanted to talk about is something called persistence. So over here, you'll see I've been clicking this button, but it's been hovering around this thing called persistence. Now, what that is it's basically the runtime settings that you're using. So if I go to preview, if you recall, I changed levels to 21 and like 25 or something like that. 33 and 21, okay. That's great. I want it to be 33 and 21 when I go back to preview or when I go to record. You don't want to set that every time. However, if you were to make a new subject, and a lot of people do, let's call this subject 1. I don't have a last known runtime setting for this subject. And the persistence is tracked based on the experiment name and the subject name. So what it's going to do is it's going to inherit these default values to start with. So if I go to preview, it's 10 and 10. Let's change this to 12 real quick and go to idle. So when I go back to preview, it's going to be 12. But let's say I go back to Algernon, what's it going to be? Well, it better be 33 and 21 because that's the last known setting of Algernon under the experiment setup, which it is. So that's what the best persistence does. If I pick last and go to subject 1, it's going to be 33 and 21 because that's the last known runtime setting. Okay. Okay, it did 10 and 12. So maybe I'm a little bit wrong there. Let's have it as last and go to Algernon. Okay, now it recognized it. Okay, so maybe I just misclicked earlier, but now if I say yes here, it's going to use 12 and 10 because that's the last known runtime setting that I used. And let's say, oops, that was a mistake. How do I fix this? Well, there's no, there's no indication of the settings here for the, remember that revision log for the experiment, but there is a known history here. If I click on the history dialog and say, show full history detail, and I click on one of these recordings, it'll, okay, it doesn't have any changes here, but if I go to these previews over here, one of these should have, okay, it tells me that I changed the level here for my subject 1. Okay, but if I remember correctly, okay, I remember that this Algernon recording had a good level. That was the correct level I wanted to use. I can right click and I can say use ending state, and then it's going to use the settings that I had for that recording. So it's going to be 33 and 21, which is what I wanted. And now when I go to idle, it'll hop back to best because that was the last setting that I used. That's the best setting for Algernon according to what I declared. So that about wraps up the initial training and everything that you probably need to know before doing something like an in vivo test. That's sort of the next step. And that has its own host of issues. If you've seen the recordings on RZ5, it's not going to be much different. Just make sure you measure the power. Make sure you're hooked up to the subject good. No gaps in the cannula, and you should be pretty good to go. It's not like it's calculating the signal any differently. A lot of this is in the manual. Actually, the whole thing about persistence and stuff is in the Synapse manual, not the photometry user guide. But everything we talked about is in the fiber photometry user guide in reference to the RZ10x and the fiber photometry user Gizmo.